You know that feeling when your computer finds one specific file out of millions, like instantly? How on earth does it do that? Well, today we're going to pull back the curtain on the secret sauce behind that magic. It's an algorithm that's both beautifully simple and ridiculously powerful, and it's called binary search. Okay, to really wrap our heads around this, let's forget about computers for a second. Picture this. I hand you a huge 1,000-page book, like a giant dictionary or an old phone book, and I tell you, find page 742. What's your move? How are you going to find it? So you could start at page 1, then page 2, then 3, and just keep flipping. That's what we call the brute force way. And yeah, it works eventually, but who's got time for that, right? The smart way, the way you and I would actually do it, is to just crack the book open somewhere in the middle. You glance at the page number. Is your page higher? Cool. You now only have to look in the back half. Is it lower? Great. You focus on the front half. In one single move, you just threw away 500 pages. That little intuitive trick, that's the soul of binary search. All right, so here's the game plan for today. We'll kick things off with a divide and conquer trick that makes this whole thing work. Then we'll look at 2 ways to actually code it up. After that, we'll get into why it's so ridiculously fast. We'll cover when you should and shouldn't use it. And finally, we'll go over how to avoid some really common traps. Let's do it. First up, the divide and conquer trick. Let's really dig into how this thing actually works under the hood. So what is binary search, officially? Well, it's a divide and conquer algorithm. It works by repeatedly checking the middle element of a collection and just chopping the search area in half, over and over again. But, and listen up because this is the most important part, it only works on a sorted array. That is the one rule, the absolute non-negotiable requirement. If the data isn't sorted, none of this magic works. Okay. Let's walk through an example. Here's a nice, sorted array of numbers. We're on the hunt for the number 73. So we start with the whole array, from the low end at index 0 to the high end at index 8. First step, go straight to the middle. The middle element is at index 4, and its value is 51. Now we just ask a simple question. Is our target, 73, bigger or smaller than 51? Well, 73 is bigger. So we know for a fact it can't be anywhere in the left half. And just like that, poof, we can completely ignore all those numbers. So now our search area is way smaller, just from index 5 to 8. What do? The exact same thing. We find the new middle, which is at index 6, and the value there is 87. Okay, is our target, 73, bigger or smaller than 87? This time it's smaller, so we know it has to be to the left of 87. And boom, we get to throw away the entire right half of our new range. Look at that. In just 2 guesses, we've gone from 9 numbers down to just 1 possible spot. Our final range is now tiny. It's just index 5. So the middle of that range is just index 5 itself. We check the value and it's 73. And our target is 73. We've got a match. We found it. Think about that. We started with 9 numbers and it only took us 3 checks to find the one we wanted. That is the power of divide and conquer right there. Okay, that's the concept. But how do we actually write the code for this? Well, there are 2 main ways to do it in a language like Java, the iterative way and the recursive way. The iterative approach is probably what you'd think of first. It just uses a while loop to keep track of the low and high pointers, shrinking the window until it finds the answer. It's super efficient with memory. We call that O1 space. The recursive approach is a little more elegant, maybe? The function literally calls itself, but with a smaller piece of the array each time. The trade-off is that it uses a bit more memory on what's called the call stack. Honestly, most of the time, that iterative loop is the more practical choice. Now, I gotta show you this. This is a real pro move. A little detail that can save you from a really sneaky bug. You might think the obvious way to find the middle is just low plus high, divided by 2, right? Well, what happens if low and high are huge numbers? Like really, really big? Adding them together could actually be too big for the computer to handle, causing something called an integer overflow. The program just breaks. This other formula, low plus high minus low divided by 2, does the exact same thing mathematically, but it avoids that big addition. It's a safer, much more robust way to write it. All right, we know how it works, but now for the really cool part. Why is it so ridiculously fast? This is where we get into a mind-bending concept called logarithmic time. Just look at this chart. It says it all. If you have 1,000,000 items and you're looking for just one of them, a linear search, that one-by-one method, could take you up to 1,000,000 checks in the worst case. Binary search? It'll take about 20. I'm not kidding. Let that sink in for a second. 1 million versus 20. That is an insane difference. If you double the list to 2 million items, binary search just adds one more step. It's a total game changer. In the world of computer science, we have a way to talk about this efficiency, and it's called Big O notation. The best case for binary search is O1. That means you get super lucky, and the element you're looking for is the very first one you check. But what's amazing is that both the average and worst case scenarios are O log n. That log n is the mathematical way of saying it's going to be incredibly fast, and it barely gets slower even when you add tons more data. So this thing is a speed demon. You're probably thinking, I should use this for everything. But hold on. It's a specialized tool, and you have to know when it's the right tool for the job. So where does binary search really shine? Well, its ideal home is a big collection of data that's already sorted and doesn't change much. It's perfect for things like quick membership tests, just answering yes or no to the question, is this item in the list? It's also great for finding the right spot to insert a new item to keep the list sorted. Basically, any problem where you can repeatedly ask, is my answer higher or lower, is a potential candidate. This little table is a fantastic cheat sheet. If your data is large, sorted, and not changing all the time, binary search is your hero. If your data is small or it's not sorted, honestly, a simple linear search might be less of a headache. And if you need the absolute fastest possible lookups and you don't care about order at all, then you're looking at something like a hash table, which is a whole other beast. The key is picking the right tool for the job. Okay, last big topic. Let's talk about how to not mess this up. Because while the idea of binary search is simple, writing a bug-free version from scratch can be surprisingly tricky. So let's go over some pro tips for avoiding the common traps. Okay, if you forget everything else I say today, please remember this one thing. The number one rule, the golden rule, the only rule that really matters. Your data must be sorted. Seriously, if you try to run binary search on unsorted data, it's not just going to be slow, it's going to give you complete nonsense for an answer or just plain not work. Sorted data is the price of admission for all this speed. So besides the big sorted rule, there are a few other little gremlins to watch out for. These things called off by one errors are super common, like setting your high pointer to mid instead of mid -1. It seems small, but it can break everything. Using the wrong loop condition, like less than instead of less than or equal to, can make you miss the answer entirely. Also, be careful with duplicates. A standard binary search will find an instance of the number, but it doesn't promise it'll be the first one in the list. So here's the real-world takeaway. It's super important to understand how binary search works, but when it's time to actually use it in a project, don't write it yourself. Just don't. Your programming language, whether it's Java, Python, or whatever, has a built-in version that's been tested to death and is probably more optimized than what you or I would write. Use the built-in one. It's your bug-free, reliable best friend. When you really think about it, binary search is more than just a piece of code. It's a whole mindset. It's a way of thinking about problems. It's about not getting overwhelmed, but instead intelligently cutting a problem in half again and again until it's small enough to solve. So the question I want to leave you with is, where else in your life can you apply that same divide and conquer logic? What big, scary problem could you tackle by just making one smart cut at a time?